I want to welcome everyone. Thank you for joining today's webinar, How to Protect Your Industrial Control Systems / SCADA Systems Using Cryptography, co-hosted by ISA and AutoSol. I'm Michaela Cooper with ISA, and I'll be hosting today's webinar. And before we get started, I'd like to review just a few housekeeping items so you know how to participate in today's webinar. First, in regards to the question and answer session, we do have one Q&A session at the end of this webinar. And to submit your questions, you'll just want to enter those into the Q&A box, and that's on the right-hand side of your WebEx screen. I ask if you're having any technical problems with WebEx, don't use the Q&A box for that. Send those in to me using the chat box. We want to reserve the Q&A box only for the Q&A questions. And if we're unable to get to your questions at the end of the webinar, then we will give you the presenter's contact information so you can contact them directly and they can answer those questions for you offline. Second, for those of you who just joined, we want to remind you to stay on mute. And if you want to see those phone and audio broadcast instructions again, just refer to that confirmation email that I sent to you today. Or if you go to the Event Info tab on your WebEx screen, that information is also given there. And additionally, once this webinar closes, a survey should pop up in your browser, and we ask that you take 1 to 2 minutes. It's not a long survey at all. And just tell us how your experience was in today's webinar so we can better improve our webinars for the future. Okay, now I think that takes care of all the housekeeping matters. I'd now like to go ahead and introduce our presenters. First, we have Ronald Krutz. He is a Chief Scientist at Security Risk Solutions. He is a registered professional engineer. He is also an author of 16 cybersecurity texts, former Carnegie Mellon faculty, and former Gulf Oil research staff. Ron is currently working with ISA on the second edition of his book, Industrial Automation and Control Systems Security Principles, Protecting the Critical Infrastructure. So be on the lookout for his new book coming out in the next few months. Next, we have David Blanco. He is an application security engineer with AutoSol since 2011. He has a master's in international affairs from Texas A&M University. His thesis project was to present strategies for negotiating with Iran to the State Department. He co-authored a paper on the topic U.S. Strategic Options for Iran, which won the 2014 Symmetric ASPA Award. He has several years of experience doing development and integration work on SCADA systems. He recently presented a white paper on cybersecurity to the International School of Hydrocarbon Measurement. He now joins us out of his office in Houston, Texas. We're so grateful to have both of these two individuals present with us on this webinar today. And I'd like to go ahead and pass it off to David to go over our agenda slide and kick off this webinar.
Thank you, Michaela, and thank you, Dr. Krutz, for doing this presentation with me, and thank you to everybody that is tuning in to this presentation from home. So here is our agenda for today. First, I'll talk about some of the challenges that we face when we're trying to secure our SCADA network. Afterwards, I'll talk about the types of threats that take advantages of those vulnerabilities. Then I'll pass it on to Dr. Krutz, who will talk about how to secure our SCADA networks with some security mechanisms like cryptography and digital signatures. And then lastly, I'll wrap it up with some brief concluding remarks before the Q&A session. So before we get too far into this, let's go over some introductory definitions. So when I talk about SCADA, I'm talking about the supervisory control and data acquisition systems that we use. A SCADA system is just any system that allows for remote control over any kind of communication channel. This could be a remote communication channel or a very short one, a direct wire. The other term is cybersecurity. So when I talk about cybersecurity, I'm just talking about the ability to protect our hardware, our software, our data, and our communication networks from purposeful and malicious misuse. So here is an image of a typical SCADA network. Normally there's a program logic controller or a PLC or maybe a remote terminal unit, RTU, that is on site where our field assets are. These devices then communicate over the field network to some kind of polling engine, polling server, or SAP server in the SCADA department of the office. The data passes through a gateway. After it hits the polling server, it goes to a human-machine interface. This is normally a controller station where the controller can read data from the field in real time and send commands back out to the field that are then acted on in real time. From there, the data can be passed on to the business network for a variety of purposes. But now it's important to note that within the context of this presentation, when we talk about SCADA security, we don't mean security of this entire network. We don't mean security on the business side of the network. SCADA security here refers to the ability of the field network to guarantee the integrity of the data and therefore guarantee the safety of the system. Now, we can maintain this integrity with security, because without security, our field assets and our SCADA network is vulnerable to manipulation, corruption, and even destruction. Security for the field assets that communicate over the field network is actually the most important part of SCADA because it is the most vulnerable. And this is a point that I hope to get across during this presentation. I want this presentation to be more like a conversation with you about security from SCADA's perspective, where we view SCADA as something that is separate from IT, and we view SCADA that is something that is under attack because it is actually underprotected. Now, every company is different, but there's normally somewhere along this line where the network stops being the responsibility of the SCADA team, of the IT department, and starts being the responsibility of the SCADA department. And drawing that line is a little bit like art. You just got to draw the line somewhere sometimes. So where is that line drawn for your company? Is IT responsible for only the business network, or is IT only responsible up to the controller's box to make sure that they have the ability to control the field? Or is IT in charge of the entire network except the assets that are actually in the field? This is a very difficult question to answer, and I'll give you a real-world example of how this actually plays out. Let's say you have a primary polling server, which is just a server that actually retrieves the data from the field, and you have a backup polling server. Now, it's very important that the primary and backup servers communicate to each other to know which one is the primary, which one's on. If there's a communication error between these two servers, that's generally an issue that can be solved by IT. However, if your primary polling server cannot connect to a device in the field for whatever reason, that is generally going to be an issue that is handled by the SCADA department. So here we have a very interesting phenomenon where IT and SCADA have different responsibilities, but they share assets, which brings up an interesting question. What happens in the situation where the business needs of the SCADA department conflict directly with the IT security protocols? Generally, SCADA wins, and I'll give you a real-world example for that. Let's say you have a controller sitting in front of his control box, and he's on the phone with a technician who is on an offshore platform trying to get some new assets to talk. A storm is rolling in, and the helicopter is about to take off, and they need to get this device talking right now because to send a helicopter back out is a lot of money. The controller, if they're having trouble because of security policy, will pick up the telephone, call IT and go, hey, I got a man out there, I need this problem solved ASAP. And more likely than not, IT will make a security exception to the SCADA department. So in this case, what happens if the network is penetrated because of the security exception made in order to get the SCADA asset talking? Is it SCADA's fault? Is it IT's fault? It may seem counterintuitive, but as IT and SCADA departments seem to share more and more technology, this is not driving them closer, but it's actually driving them further apart. I call this phenomenon the IT-SCADA gap. But before we get too far into that, let's take a quick poll. In your opinion, are the duties, responsibilities of your company's IT and SCADA departments clearly defined so as to create a clear chain of security protocols and responsibility for the company's SCADA network? A, yes, A, no, B, yes, or C, some. And if you take time to reflect on that answer, I would just like to say that if you have any questions about anything you've seen during this presentation, especially in the months to come, I will be at ISA's Process Control and Safety Symposium on the 7th to 10th of November in Houston, Texas. So please feel free to come on by and ask me anything that you can think of if it's regards to this presentation or anything that involves SCADA security. So I think we've had enough time to get some answers in. So let's see what the poll results are real quick. Well, while that processes, I'll go ahead and say a little bit about the examples that I'm pulling up during this presentation. I work in the oil and gas industry, so that's where most of my examples come from, and that's where most of my perspective is right now. All right, so it looks like most people say no, with a few yes. Well, I hope that those of you who answered no and some are able to learn a lot from this presentation, and even those of you who answered yes still get something out of it. Now let's talk about the IT-SCADA GAP. So what is the IT-SCADA GAP? This gap is the empty page on your handout during your cybersecurity meeting. It's that place where IT-SCADA solutions fail to address SCADA security problems. Now, this gap does not exist because someone has failed to do their job correctly. On the contrary, this gap exists precisely because everybody, SCADA and IT, both do their jobs and they do them well. So what exactly makes up the policy gap? The policy gap exists because SCADA and IT both have different assets. Although they share a few office things, generally their focus is on different assets. They also have divergent goals. SCADA has a minimalist approach to technology adoption, and there are drastically different results of a breach in each case. So now let's talk about the first one, the different assets that make up the IT-SCADA policy gap. IT, and of course this is in relation to SCADA only, IT generally uses the latest and greatest hardware and software that money can buy. Usually the hardware and software is deployed directly in the office where the IT department is themselves. SCADA, on the other hand, often has its assets scattered around the globe, sometimes even being hundreds or even thousands of miles away from the SCADA stakeholders themselves. What this means is that it is extremely hard, both logistically and financially, to maintain and sometimes even access these assets. As a result, SCADA assets are often designed differently than IT assets because they have to work in rugged environments and sometimes work with very little power. So they're usually designed with lifespans of 15 or even 20 plus years, which makes a very interesting situation. So here we are trying to defend these legacy SCADA assets from security threats that literally did not even exist when these devices were created. So what this means is that there are some defensive gaps between what IT can do and what SCADA can do. And a good real-world example is the reaction time in the event of an attack. So IT, and again in relation to SCADA only, IT can react to a breach of security relatively quickly. They can isolate the infected hardware, they can replace the hardware, replace the software very, very quickly, or even upgrade and get new equipment. SCADA, on the other hand, cannot access its assets that quickly. And at the time of I was doing the research for this presentation, there were 35 known cybersecurity vulnerabilities from 9 unique vendors of hardware for the oil and gas industry, which is testament to how difficult it is to actually patch security issues on this kind of hardware. The next issue between SCADA and IT are the divergent goals of each one. So generally, so long as data comes in, nobody really questions the network's configuration. And this is because IT and SCADA have different jobs. SCADA's job is to make sure that the field devices or the SCADA assets work safely, that the data that they receive is reliable, and that the data that they want to transmit is actually transmitting. IT, on the other hand, needs to keep the company running by facilitating communications and providing security for office emails. Technicians don't get angry emails from their superiors if data comes in too quickly or too reliably, and IT doesn't get a pat on the back when they block the IP addresses of field assets. So here we have a situation where SCADA adopts only the latest and greatest communication technology it can without the ability to bring along the partner security technology. This is a minimalist approach to technology adoption. So basically, SCADA has been able to employ the latest and greatest, or the cutting edge, communication technology to give fields that used to not even be on a map are now mapped on some kind of global network. but unfortunately, sometimes the cutting edge of technology turns out to be a double edge. So they rely on outdated defenses in order to defend the assets from hack attacks. And I'll briefly go over some of these. The first outdated defense that many SCADA systems rely on is security by obscurity, or the hope that your IP address is so hard to find that no one will ever stumble on it unless they know where it is, or that your assets are so uninteresting that nobody wants to find it. Now, in 2012, there was a census of the internet taken where they found 93,000 devices listening on Modbus TCP/IP port 502 available on the public internet. What this means is that attackers don't actually have to even go through your IT department in order to access some of your assets. As we found out, there are 93,000 devices sitting on the open internet waiting for anybody to access them. The other outdated defense is air gapping. Air gapping is basically trying to isolate your SCADA network from other networks, your SCADA network from your business network or what have you. Now, this used to work, but it is no longer a viable defense. And of course, the greatest example of this is Stuxnet. Stuxnet is a piece of malware that infected the Iranian nuclear facilities in Natanz. Now, that facility is literally underneath a mountain, and the network that the facility was running on was isolated from the internet. But somehow, Stuxnet still managed to get on the system. That's because there came a point where data had to be transmitted from outside the network or inside the network, and a USB stick was used. And on that USB stick was Stuxnet. So air gapping is often overcome by those kind of connections, by USBs, and even in our own companies, I'm sure that there's some point where data has to get out of the SCADA network to a business network. Now, we may think that we have those choke points guarded, but the Department of Homeland Security of the U.S. did an audit of industrial control systems recently and found that even on companies that said that they had no direct connections or that they were heavily monitored, were actually unable to track how many connections they had. Pictured below there is a man named Sean McGurk as he testified before the U.S. Congress on the state of industrial control systems or SCADA systems security. He was the acting director of the National Cybersecurity and Communications Integration Center at the Department of Homeland Security. And during his testimony, he said, quote, "In no case have we ever found the operations network, the SCADA system, or energy management system separated from the enterprise network." He continued, "On average, we see 11 direct connections between those two networks, and in some cases up to 250 connections between the production and the enterprise network." So with the hyperconnectivity that we get with modern communication technologies, we also get holes in our network that we can't plug safely. The other outdated defense is an over-reliance of safety logic. So safety logic is logic that is running on a device on the field site that makes sure that if a tank is at a critical level, like too high of a level, that the pump won't turn on to pump more liquid into the tank. But when you use safety logic as a defense against hackers, you're missing the point of safety logic. Safety logic is there to protect assets from automation, and to protect assets from user error, not protect assets from malicious misuse. Relying on safety logic as a defense ignores the possibility of the hackers actually having the SCADA knowledge required to manipulate or override the safety logic. It also rather unfairly shifts the burden of defense for your network onto the hardware manufacturers themselves. A lot of these devices are not designed to handle security. They're designed to be deployed remotely and sometimes in places with very little access to electricity. So they have to use the least amount of computing power possible in order to achieve their goal. It also may take years to develop a countermeasure to a security vulnerability on these devices because of those conditions I just mentioned. And again, I'll use Stuxnet as an example. One of the ways that Stuxnet did damage to the Iranian nuclear facility was by infecting a transmitter that is also commonly used in the oil and gas industry. And it sat on the transmitter, it recorded good data, and played back the good data during an attack. Once this vulnerability was revealed, it took the manufacturer of that transmitter 2 years to come up with a security solution for that vulnerability that Stuxnet took out. And imagine how much longer it would take you, had you had that transmitter, to deploy it to all your assets in time. Now, that's the last of the outdated defenses. Now we'll talk about the very last peg of the IT-SCADA policy gap, and that is the different results of a breach between IT and SCADA. Generally, when IT is hacked, the damage can be measured in dollars. But when SCADA is hacked, more often than not, the damage can be measured in lives. The goal of hackers when they hack IT is usually to get money or to get some kind of information. If there's damage, it's usually only to reputations and maybe even servers. SCADA, on the other hand, is special. SCADA straddles the divide between the cyber world and the real world. When a controller sends a command out to the field, that electronic signal is translated by the assets into some kind of kinetic motion. This can be as drastic as someone opening up a valve and turning on a pump to feed oil into a tank until the tank overflows and explodes. And what's key about this is that when SCADA is attacked, it's attacked because the hackers don't want information about the assets. At the end of the day, they want the ability to control the assets to destroy themselves. This means that there's really no second chance when it comes to SCADA security. How many times can a tank be blown up versus how many times can an IT server be infiltrated? Because there's no second chances, prevention is absolutely key when it comes to SCADA cybersecurity. Now let's take a moment for another poll. This one's very short. In your opinion, do most SCADA systems have adequate security protection in place? A, no. B, yes. C, some, but not adequate in all situations. I know from some of my experiences that even on systems that think that they have some kind of security protocol deployed, that's more of a just a paper coating on the reality, because the hustle and bustle of the day and the complex nature of trying to get devices to poll sometimes means that you bypass security in order to get something talking, and then you immediately have to move on to the next issue. I think we've had enough time for that poll. Let's see some of the results. And while the poll's ended, it looks like it's just calculating up. Take a quick drink of water. All right, and it looks like a majority of y'all said no, and only 1% said yes, which I guess makes sense because that's why everybody has tuned into this webinar. So now let's talk about the threats themselves. Now we have a better idea of what the vulnerabilities of our SCADA systems are. Let's talk about how threats take advantage of those vulnerabilities. Now, a lot of times when you talk about SCADA security or you try to have a conversation about SCADA security with SCADA stakeholders, some people say, well, you know, I don't actually think that SCADA is going to be hacked because really what's the motivation? I mean, you can't get a credit card number off of a pump jack. Other people say, well, actually, I don't think SCADA can be hacked because it requires such a specialized set of skills to know what you're doing, to know how to open a valve, the right protocols, find the right assets. It's hard enough getting it to work for us, let alone how's a hacker going to do it. Now, what's interesting about these arguments is that they're not designed to actually solve anything about SCADA security. They're designed to shut down any discussion about SCADA security. This is very problematic because if you don't actually talk about the capabilities of hackers, then you can't talk about how to actually stop them. You don't want to be caught with a knife at a gunfight. The discussion we need to have is, who are the hackers? What can the hackers actually do, and where will they actually strike? When we know all of this, then we know not only where to put our defenses, but what to do to defend ourselves. So let's talk about the evolving threat to SCADA. Last year, there were 675,186 attacks against SCADA networks in the U.S. Now, this is more than double from the year before, which itself is more than quadruple from the year before that. So what we see is this increasing number of attacks each year, this upward trend. And now the attackers would only be increasing their number of attacks if they were getting something out of it. So obviously, they're getting a return on their investment, or they perceive that they are. And this number is also, this 675,000 number, is also severely underreported. That's because in the U.S. at least, a company only needs to report that it's been hacked if the hackers steal personal or financial information. So this number is severely deflated in my opinion. Now, Stuxnet, again, is very important to this conversation because Stuxnet is the very first known piece of malware to physically do damage to a SCADA system. And it was so successful at duplicating itself and spreading on Iran's network that it eventually leaked out of that network, infecting tens of thousands of other devices. Once it infected these other devices and was discovered, its source code was loose. So we see Stuxnet being used as not only a policy touchpoint proving that you can actually hack SCADA, but also providing the source code to a lot of copycat attacks on how to actually do it. And because Stuxnet was able to anonymously damage the infrastructure of a government, it attracted a lot of other governments because being able to attack critical infrastructure at a time that is valuable to you is an opportunity too great to miss. So what we see is an increasing role of government in attacks against data. As of the research done for this presentation, there were 140 governments with a known offensive cyber capability. We've got the US, Israel, Iran, Russia, China, North Korea, and even Tunisia. So what we see here is Stuxnet as a hacking touchstone and the kind of resources that only governments have being brought together. What this means is that they can bring together the people who have the hacking skills with the people who have the SCADA knowledge. So really, when it comes to SCADA security, it's no longer just your IT department or your SCADA department against a lone hacker or a small group of hackers. It's you versus the hostile enemy government's military. It's a David and Goliath story, except in this story, Goliath has a bigger sling. So let's talk about some of the threats that we've seen since Stuxnet. Now, Stuxnet affected some countries harder than others. And the country that learned the hardest lesson from Stuxnet very quickly invested $1 billion for an offensive cybersecurity capability in 2011. What you see there on the chart on the right, on the right side of that chart, is every attack by that particular nation since 2011. As you can see, they've been quite busy. And the most interesting one is Operation Cleaver there on the bottom, the fist holding the cleaver. That was a 2-year hack until it was discovered. It is essentially a way for the hackers to methodically probe every nook and cranny of a SCADA system. That malware came with a screen cap and keylogger, so that way they can obtain the login screen and credentials of controllers. During that attack, they also stole engineering documents of a, quote, mission-critical nature. I guess they wanted to know exactly what they should be trying to get a hold of before they continued their hacking job. But luckily, they were discovered before any damage could be done. Another example is in 2012, a group of researchers in the US set up a decoy water plant that you would find in any kind of moderately sized town in the US. Shortly after coming online, hackers from a certain nation's military began to take control of the assets and probe it and send commands open, shut, to kind of gauge what kind of devices they were working with, how many valves they had, how many pumps they had, etc. And to quote the MIT Technology Review about this incident, the attacks displayed a high level of knowledge about industrial control systems using techniques to meddle with specific communication protocols used to control industrial hardware. This attack is interesting for 3 main reasons. The first one is that it proves that SCADA assets themselves are being targeted. Someone is out there scouring the internet for every single open IP address possible, and then when they find SCADA assets, they have the people on hand to actually control it. The other point is that they did not have to go through an IT department in order to gain access to the assets. They just used the open internet. And the third point I kind of already alluded to was that the foreign government that did this hack was able to create a great amount of synergy between the hackers who actually found it and the people with the SCADA knowledge. Another example comes from Europe with the Havix worm. Now, the Havix worm is pretty much a cut-and-paste copy of Stuxnet with a few tweaks. It actually tried to gain access to field assets using OPC communication technology specifically. But luckily, it was detected before any damage could be done. However, that's not always the case. In 2016, January of this year, in fact, a Ukrainian power grid was hacked and shut off power to 80,000 people in the dead of winter. Last year, a German steel mill was hacked. Essentially, hackers penetrated the SCADA system of a German steel mill and prevented controllers from turning off a blast furnace at a critical moment during a procedure. The result was a, quote, massive explosion, which was very hard to find details about, as I believe a lot of the details are still under investigation by the German government. So, we've seen a lot of hack attacks, but why haven't we seen more? You may be asking yourself, if we're so vulnerable and the number of attacks is so high, why don't more things explode? I believe the answer to that question is because hacking SCADA is more of a strategic weapon. Governments are going to destroy SCADA assets when there is the most political, the most economic, or the greatest military advantage possible. It's kind of like how sometimes countries send bombers to other nations' borders, or sometimes they send bombers over other nations' borders. What they're doing is they're gauging the defensive capabilities of that government, so that way they know when it comes time to actually launch an attack, what do they have to do to make an attack successful? And I believe the same thing happens here. Now, there are several examples also of how little resources it actually takes to attack SCADA. What I might have lost in my bombing analogy is bombers are very expensive and not everybody has them. But attacking SCADA is not an expensive proposition, and almost anybody can do it. In 2013, at the Black Hat Convention in Las Vegas in the US, it's kind of a who's who of the hacking community, there are two such examples. The first comes from two researchers named Brian Mexel and Eric Forner. What they did was they set up a small sample oil configuration on their stage. They had a bucket of water that had a tube connected to a pump, connected to a valve with a tank. And we can see that layout here. What they did was they hacked into the HMI, then they got onto the safety logic, and they rewrote the safety logic to allow the pump to be on and the valve to be open at a time when the tank was already at critical levels. So they were able to turn the pump on, open the valve, and overflow the tank. Now you might be saying to yourself, well, that wouldn't happen to me because my controllers are vigilant people and they would have seen it on the screen. But during this attack, they were able to actually feed false information to the HMI. So while the tank was actually overflowing, the HMI was showing the controller that the tank was actually losing liquid. Another example came with Carlos Pinaga and Lucas Alba. Using nothing more than a radio transmitter that they bought from Radio Shack and knowledge of the industry, they were able to take control of some remote field assets. So now we're on to securing SCADA networks. We understand the vulnerabilities of our network, and we understand how people are actually taking advantage of those vulnerabilities. However, I feel like I must give a quick caveat. It is not statistically, philosophically, or even practically possible to know every form an attack might take. This is really more of a how will they attack us rather than a, well, what if they were to attack us using this? Only by focusing on the probable can we actually achieve what is doable. Now, the methods that we will be discussing in this presentation are not the only methods available to us. However, they are the methods that Dr. Krutz and I feel are the most effective methods that can be employed by people like us. And to answer the question of where will hackers attack, because we have the who and we have the what will they attack, the answer is the field. The field is where the tanks are, the field is where the plant is, the field is where the utility station is. These are the assets that enemy hackers want to get a hold of and control and destroy. Therefore, that should be the focus of our defenses. If you don't focus your SCADA security defenses on the field assets, that's like trying to defend your garden from rabbits by putting a fence around your house instead of putting a fence around your garden. And the best way to actually provide security to those field assets is through methods of prevention. But now, when you're trying to actually prevent attacks, what are some goals that you can try to achieve? The 5 goals that we need to work for for a safer SCADA network are these: confidentiality, data integrity, authentication, authorization, and availability. Confidentiality is just making sure that only approved stakeholders have access to the data and the network. Integrity means that all the data coming from the field and all the commands going out to the field are unaltered. Authentication just means that the people who are accessing the network of the assets are actually the people they say they are. They're approved individuals. Authorization just means that once someone actually has access to your system, do they have the authorization, do they have the rights to send an open command to that valve? And of course, availability. Do you have the capability of maintaining communication to your assets in a time of crisis? And so we have one more quick poll. It has been shown by Stuxnet and other malware that USB devices, such as flash drives, are effective entry points in generating attacks against SCADA systems. From your perspective and experience, is there adequate awareness of this threat, and are there corresponding safeguards in place in organizations which you are familiar? A, unaware, B, aware but no follow-up, or C, aware and safeguards are in place? All right, let's go ahead and collect our poll, and while that calculates, I will be passing the mic now to Dr. Ronald Krutz, and he will be talking about the security mechanisms that we have available to us to actually secure our SCADA assets. Those will be cryptography and digital signatures. But I'll quickly wait for the Q&A results to come in. All right, it looks like, all right, a better mix than the last question between B and C, that's for sure. All right, so without further ado, I will pass it on to Dr. Krutz. All yours, sir.
Hey, thank you very much, David. And good morning, everyone. David has certainly provided incentives for addressing SCADA system security, but first we'd like to establish some common terminology before we get into cryptography and digital signatures. So what we want to cover on this slide is the terminology for threats, a threat source, vulnerability, and safeguards. Now, a threat is any circumstance or event that can have the potential to adversely impact an organization and its operations. Usually the result is unauthorized access, destruction of data, disclosure of information, or denial of service. A threat source is any threat intent or method that could exploit a vulnerability through either intentional or unintentional means. Now, it's interesting to look at those last phrases. We may have hackers that are intentionally trying to cause damage to a SCADA system, but we also could have unintentional means, and this could mean an incompetent operator, but the results could be the same. So on the next slide, we can look at a vulnerability. A vulnerability is just a weakness that can be exploited and can be triggered by a threat source. And a safeguard are countermeasures that we could put in place to mitigate the risk that's posed by a threat or a group of threats. Okay, let's take a look at some threat sources. These are typical threat sources that would be looking at attacking SCADA systems. We have your typical hacker or cracker, and what's the motivation? Sometimes it's just ego to see if they can get in, or it could be a rebellion in a country. Now we have computer crime, where information can be destroyed or sometimes exploited for monetary gain. There seems to be a lot of publicity lately about ransom, where attackers will encrypt data and will not provide the key unless the data holder pays a ransom. Terrorists, I think we're familiar with that. And also industrial espionage, where a company might want to get a competitive advantage on another company. And again, we could have insiders or poorly trained employees, disgruntled employees who try to get back in an organization. Okay, let's take a look at some SCADA system threat incidents. A typical one is a denial of control action, which is pretty clear in the statement. It tries to prevent a control action that's required from being executed. We can have control devices being reprogrammed, so SCADA system elements will perform different functions than they were designed to do, obviously causing damage or even loss of life. As with Stuxnet, as David described, we could give spoofed status information, so the system can be crumbling underneath you, but the signals tell the controllers, the operators, everything is fine. And we can also manipulate the control logic to produce some harmful results. Safety systems usually work in parallel with the security systems, so they can be spoofed to not detect emergency situations. And malware can be installed on control systems, as David describes with Stuxnet. Okay, let's stop for a poll question. We all see this happening more and more. Everybody is bringing their own devices into offices, into plants. So wireless devices such as tablets and iPads are increasingly being used to interface with control systems. In your opinion, do these off-the-shelf products offer adequate security protection for use in the SCADA systems? A, no. B, yes. C, some, but not adequate in all situations. Yeah, this is a very timely question because there are usually unauthorized mobile devices brought into plants. And again, as shown with Stuxnet, a flash drive can be used to introduce malware. We'll see what the poll results are shortly.
Okay, I know you're having
waiting, issues. Let's bring up the next slide.
I was going to say, I know you're having issues seeing WebEx, but we're at 65% no, 3% yes, and some 31%.
Thank you. Let's get into controls. Controls are things we do to prevent attacks from happening. Now, there are 4 general categories of controls that are referred to in the methodologies. Preventive controls, these are the ones we like the best. We want to prevent a threat from exploiting a vulnerability in the first place. Corrective controls, we want to reduce the effect of an attack and minimize the resulting damage. Detective control, we want to see if we can determine if attack is underway. And if we do, try to initiate some control measures. And deterrent controls are to reduce the potential for an attack to occur. Okay, next slide, we will look at a threat matrix. As in any organization, there are limited resources, and the SCADA systems, as David discussed, there are limited computing resources. Sometimes in legacy systems, there's not a lot of cycles left to do much of anything else except worry about controlling the process or the manufacturing operation. So a threat matrix allows us to try to prioritize where we focus our limited resources. The two interesting quadrants are the top right, where the threats will have a very high impact on our organization and have a very high likelihood of occurring. Now, the lower left quadrant are threats that have a very low impact and a low likelihood of occurrence. So the objective is to move the threats from the upper right-hand quadrant down into the lower left quadrant with the resources we have. Okay, we'll look at some important effective controls. There are obviously many different types of controls we can apply to try to protect SCADA systems. The two we're going to concentrate on here are cryptography and its use in digital signatures. Let's get a definition of encryption. This is one we all know. The purpose is just to scramble information when it's being transmitted, and so it can only be read by the intended recipient. There are three main types of cryptographic technologies: private key, or sometimes called secret or symmetric key, public or asymmetric, and hybrid, which combines both. Symmetric key cryptography is the one we're most familiar with. A sender has a key and the receiver has the same secret key. So we protect this key. We don't want anyone to know it. So the sender encrypts the plain text message with the secret key. The receiver gets the message and decrypts it with the same secret key. The problem with this methodology is we have to safely and securely get the key from one person to the other, or one person or one individual to the other. That's usually best done out of band, so you don't send it in the same channel where you are sending the message. The National Institute of Standards and Technology has come up with a very good secret key algorithm, the Advanced Encryption Standard, AES, and you see this all the time, even when you're setting up your router or other devices. In government uses, it's used to protect sensitive but unclassified information. It's widely used in commercial and industrial applications, and its specification is under FIPS publication 197. Here's a diagram just graphically showing what happens in that symmetric key cryptosystem. We have a plain text message that's encrypted with the secret key. The ciphertext or scrambled message is sent on an unsecure channel. The receiver has the same key, decrypts it, and reads the message. Now, public or asymmetric key cryptosystems solves the problem of key transfer. Now, to do this, it employs two keys, a public key and a private key. And these two keys are related mathematically. So the public key is just what it says. It's made available to anyone wanting to encrypt or send a message. So if you want to send me a message, my public key is out there for anybody to get, and they can encrypt the message with my public key. Now, once the public key encrypts the message, it cannot decrypt it. So anyone out there who grabs the public key cannot decrypt the message. The only key that can decrypt that message is its companion private key. So the receiver has that key, they keep it secure, and it's used to decrypt a message. Now, one very important element is the private key cannot be derived from the public key. So there are very a number of different types of algorithms, integer factorization, discrete logarithms, or elliptic curve relationships, but complex mathematical methods that are used to generate these keys to make it very, very difficult or impossible to determine the private key from the public key. You could probably do it, but it might take hundreds of years. So this eliminates the need to exchange secret keys. Okay, on the next slide, we see that one other important characteristic, a message that is encrypted by one of the keys can be decrypted with the other key, so it can work in the reverse situation. Again, it's important that the private key is kept private. Okay, here the next slide has a diagram of public or asymmetric key cryptosystem. A person who wants to send a message to a receiver obtains the receiver's public key, which is out there and available, encrypts the message, the ciphertext is transmitted, and the receiver uses his or her private key to decrypt the message. Now, that private key is the only key that can decrypt it. On the next slide, we have a reverse procedure. What if the sender encrypts the message with his or her private key, and the receiver can open the message with the sender's public key? What this does, it authenticates the sender, because that public key can only open a message that's encrypted by the private key. Again, they are a key pair that are mathematically related. So if the public key opens that message, that tells you who the sender was. It authenticates the sender. And we can use that in digital signatures. So that activity is shown here in this slide. The sender uses his or her private key to encrypt a message. The encrypted message is sent. The receiver gets the sender's public key, which is readily available. And if that key decrypts the message, we know that it came from the sender. On the next slide, we have a nice approach. We have a way of using both of them together. Symmetric key cryptography is very good for transmitting very high volumes of data and working very rapidly. Since public key cryptography uses a number of mathematical functions to encrypt and decrypt, it's much, much slower. So it's not very good for transmitting a lot of information. So we can get the best of both worlds. We can use public key cryptography to send the symmetric secret key that both the sender and receiver can use. And then we use that to decrypt a secret key transmission. Now, one thing that's important is we can put timestamps on this session key so that someone can intercept it and use it later. It's only valid for a certain period of time. Okay, before we go farther, let's look at another poll question. And this is something that we hear a lot of in SCADA installations. Equipment is installed, and there are factory settings and passwords that are left in place. And there are also back doors that the manufacturer has into the equipment that remain open, that can be compromised. So in your opinion, do most SCADA systems remain deployed with factory settings and passwords? No or yes?
Okay, and we are at 26% no and 72% yes.
I expected that. That is a very, very common vulnerability. Okay, going on to the next slide. We can use the technology we just described to authenticate the source of data, but also we want to verify the integrity of the control system data. So if we can use some methodology to authenticate the source of the information so it can't be spoofed by a hacker and know that the data has not been changed, this is a very valuable capability, and digital signatures provide this capability. Okay, what is a digital signature? Well, it's not constant. It's a function of the document which it signs. It's a function of the entire document. This is an important point to grasp. We can have a very, very large document. We generate a digital signature. If you change one bit in that document, the digital signature changes. So how do we generate this digital signature? A hash function provides this capability, a hash function which generates a message digest, and that's shown graphically on the next screen. What is a message digest? It's a fixed size result of applying a hash function to a message. So we can have, we look at the diagram, a very, very, very long variable length message. We put it through the hash function, and we come out with a relatively small bit string of fixed length, which is the message digest. Again, the important point to note is this message digest is a function of the whole length of the large message. So we change one bit in the variable length message, the message digest gets changed. So we can use this for integrity. So, as shown on the next slide, any modification to the message being sent to the receiver results in a different message digest being calculated by the receiver. The receiver gets the message, puts it through the same hash function, and compares it to the hash function which was sent by the sender. If the two don't match, there's a problem. Again, NIST has some algorithms. A very popular one is the SHA-2 secure hash algorithm. And if you look at this, this is interesting. Any message less than 2 to the 64 bits can be used as an input and generates a message digest that you see here, 224 to 512 bits. Very much smaller than the original message. The next slide shows that graphically, a digital signature graphically, the sender has a message, puts it through a hash function. A hash function is more like an encryption. It just scrambles the data but produces this fixed length message digest. The message digest is encrypted with the with the sender's private key. So the digital signature, which is the message digest, is attached to the message and sent on to the receiver. So in the bottom part of the slide, the receiver receives both the message and the digital signature. The receiver takes the message, puts it through the same hash function, and a message digest is generated. It also decrypts the digital signature with the sender's public key, which authenticates the sender, and gets a message digest. The two are compared, and if they're not the same, we know that the integrity of the data has been corrupted and there's something been modified in transmission. Okay, this next slide summarizes the digital signature application to SCADA systems. It provides confidentiality because we use symmetric key encryption. We can authenticate messages. The private key of the sender can only be opened by the sender public key. This gives us our authentication. The message digest verifies the integrity of the messages, and it also provides non-repudiation. What that means is the sender cannot deny sending the information because we use the private public key pair to check that. All right, I'll turn the next slide over to David, who will summarize the application of this to SCADA systems and conclude the talk.
Thank you, Dr. Krutz. That was a very good presentation. So to conclude this presentation, so far we have discussed all the ways in which our SCADA networks are vulnerable. We talked about the IT-SCADA policy gap, how IT and SCADA have different assets, they have divergent goals. SCADA usually tries to get the least amount of technology required in order to fulfill its job, and that there are different results of a breach in case of an attack. We then talked about the different threats that actually take advantage of those vulnerabilities. We talked about a number of examples of SCADA systems specifically and theoretically. And then Dr. Krutz talked about the security mechanisms that we actually have at our disposal to make our system safe. Now, these recommendations must become part of a network in order for that network to truly be a SCADA network. After all, if you do not have safe supervision of your network and you don't have reliable data, then all that's really left in SCADA is control. And then the question is, who is really in control? And with that, I will pass the mic on to Michaela for the Q&A session.
Great. Thank you both for such an amazing webinar. And now we're going to open up for the Q&A session. And while those questions are filling into the Q&A box, I'm just going to give another reminder about ISA's Process Control and Safety Symposium and Exhibition. And that is November 7th through the 10th in Houston, Texas, in the U.S. So come out and join us. Registration is open. Go to the ISA's website and register now. Visit ISA and the AutoSol team there. Okay, I'm going to go ahead and pull up the Q&A and read the first question. Okay, do you think that wireless transmitters is more prone to attack than wired?
I'll go ahead and give a brief answer to that from my perspective, and then if Dr. Krutz would like to also give his opinion. From what I've seen on remote oil and gas sites at least, generally no. The kind of wireless transmitters that, well, first let me tell you how I'm interpreting the question. I am interpreting the question as an on-site question. So if you have wireless transmitters from one asset to another on-site, is that a greater security risk than a direct wired connection? My answer would be no. Those wireless devices often have a very short bit of communication length. So if someone's close enough to hack into those on-site, there are other issues to worry about. And if we're talking from the field assets all the way to the office, no, I do not believe that the wireless or wired has more or less advantages over the other one, because at some point there is going to be a wired connection, and at some point there is going to be a vulnerability generally onto some kind of network. It could be the open internet itself. So if you have a field asset that's using wireless communication to talk to something that is maybe a couple miles away, and then from there it's wired, then the vulnerability exists on anything that touches that wired network, and I don't believe that the wired would be intercepted in the way that we're talking about in this presentation. Dr. Krutz, would you like to add anything on that?
I might modify that somewhat. I agree with you. If it's an internal situation to a plant, it's probably minimal, but if it's being broadcast over a distance, remember it's a radio and it's sending out signals, and it's being received by a receiver. So you have this radio being transmitted. It can be picked up by anyone, and I think it can be used, there are some vulnerabilities that can be used to intercept that information, say very simply, just jam it and prevent it from getting anywhere, which could cause a problem. So I think if you're talking about distances and you're broadcasting information on a radio transmitter that anybody can get to, I think there are some concerns in that matter. And you would like to, again, you want to have encryption. You know, they use, you can use encryption mechanisms on transmissions to protect that. So, you know, there are technologies that are available to use that. And, you know, even cell phones use frequency shifting devices, which aren't completely secure, but I would say if you were going to transmit critical information over long distances, one, you should worry about jamming, and two, you should worry about encrypting the data so it can't be spoofed.
And if I can just make one comment there, I see a number of questions popping up about very, very specific hardware and software questions. It is not the place of this webinar to mention any products by name. So if you have any questions about specific hardware or specific software, you can direct them to Dr. Krutz and I directly through our contact information after the webinar.
Great, thank you. Okay, and if any of those questions pop up that I read out, then we can also just defer those. Next question, what is the difference between SHA-1, 2, MD5 hash methods? Is any one better?
Can you repeat that, please?
What is the difference between SHA-1, SHA-2, MD5 hash methods? Is any one better?
Well, SHA-2 is a very popular one. I won't get into the technical details of each. SHA-2 is very widely used and very popular. SHA-3 is now in draft form and being worked on, which will probably replace SHA-3. So I would say right now SHA-2 is a good one to use.
Okay. Next question. I know we've got a lot of people internationally, so I know some of these questions may not come in correctly, but how to implement for old network system?
Are we talking about implementing encryption, or?
I'm not quite sure.
I would just say in general, and again, it is not the place of this webinar to mention any devices by name, but there are things that can be put into a field network and work with legacy devices. So that's all I'll say about that particular topic.
Okay, our next question. Many control system suppliers proposed an option of remote access for diagnostic and support, product customer support. It is usually safety concerns since they can get access to entire control system. If I need to go with it, so what is the best safe method?
I think that kind of gets back to a point I made earlier in the presentation where the job of SCADA is really to bring data in. And so a lot of the tools designed around SCADA are designed just to bring data in. Now, in order to use a technology like that, like some kind of software that connects directly to the remote unit itself for some kind of configuration or programming, without something being built in there, you would have to have some kind of cryptographic communication technology applied to the communication chain from the field to the office to make sure that whoever was accessing that device using that software was authenticated to do so, like what Dr. Krutz's digital signatures would make sure of.
If I could add to that, because that's a very common point that manufacturers like to have a back door into the system and say, well, we can provide updates that way. We can give you, software improvements, things of that sort. But again, the concern is they have a direct line right into your system. So if that line is hacked or compromised, you have a problem. So again, as David mentioned, one method is to use digital signatures where any information that is transmitted is digitally signed and has a valid certificate, so you know that it's from the source that it's from and it's not been compromised. So yeah, you can have the best of both worlds, but again, digital signatures provide a very valuable tool to prevent damage that way.
Okay, great. And you'll have to forgive me if I mispronounce any of these words. What about combination of one-way data diodes and cryptography for integrity? Is it possible?
Yes, it is possible. There are some systems that use fiber optics in order to send data from the field to the office. So they're essentially using the physics of light. Light can only travel in one direction on these devices, and that prevents any commands from being received by the field. How practical that is for people in our industry, if you have a remote site, can it handle the computing power and just the power usage of a device like that? That depends on what assets you're trying to defend, but to answer your question, is it possible? Yes. Is it practical in a majority of situations? I don't believe it is.
Okay, our next question. What are practical methods for implementing these methods in existing SCADA systems?
Talking about encryption methods. Yeah, if I'm assuming that the encryption methods, sometimes it's a problem. As I mentioned, and I'm sure David can concur, some of these legacy SCADA systems have very little excess memory and very little excess computing cycles. So if you start putting heavy encryption and decryption loads on these systems, they can't handle it. So again, in some areas it's a problem. So what you try to do, there are products. Again, David mentioned we can't get into the details, but there are minimalist products that use some of these technologies that don't require a lot of extra computational methods. Some require the addition of memory and maybe some supporting coprocessors, but in some cases it's a challenge if you can't get in there to modify things. These legacy systems sometimes are not very easily modified. Everything is hardwired. So I guess I'm saying it's a challenge, and if there are some extra computing cycles and memory, then you're in good shape, but otherwise you have to try to add some modifications so you can apply some of these digital signature technologies.
Yeah,
David, do you have anything else to add on that?
Yes, I do. So it's kind of like, if you have an old well site in the oil industry that's been there since the 70s, someone had to come along and add your radio or add your satellite link. And it's kind of the same situation here. There's got to be some kind of additional hardware deployed to the field to handle this new technology. That's the short answer of it.
All right, great. Moving on, we've got a lot of questions coming in. These are great. I don't know if we'll be able to get to all of them in this webinar, but we'll answer as many as we can. Do you feel that reducing the surface area of attack through proper architecture would be a good first step before adding cryptography?
Reducing, I guess you're talking about maybe reducing the attack the attack surface, that's a general term. Yeah, you want to reduce the attack surface by decreasing the vulnerabilities in the system. So in many cases, as again David pointed out in some of the testimony, there are vulnerabilities that exist that can be mitigated just by analyzing the system, disconnecting any unnecessary connections. Also physical prevention, having people that should not have access to an area get in there, that, physical security. Also in many situations, particularly in control systems in a refinery or in a plant where things are very critical, there are many passwords that are around, and people share passwords. You don't want to have a problem if you're trying to get into a system and there's an emergency and you can't remember the password. So sometimes passwords are very loosely distributed and given to everybody. So things like this, non-technical methods, administrative methods, and physical security methods are very effective in reducing the attack surface, and you can do this by essentially taking inventory of the safety and also the status of your system.
And oftentimes, especially in something like the oil and gas industry, again, that's where my experience has been, the network is already as small as it can possibly be. The well is where the well is, and so there's the minimum number of radios deployed out there to get the data in, and because of costs and the location, it's already slimmed down, and so there are some choke points that kind of help reduce the surface area. But I think that in terms of security strategies, yes, it's always great to reduce the surface area for an attack to actually take place on, but SCADA kind of already operates, I believe, along the smallest network possible.
All right, moving right along. Next question. While we understand the need to secure our field networks, this may not be possible due to the nature of the protocols used, example, Modbus/Profibus.
This is something that I would encourage you to contact me about after this. I have seen it done where Modbus protocols are in fact wrapped in TCP/IP, and then the entire message can be encrypted. So the protocol is not really the issue. The issue would be finding the best way to deploy that cryptology in front of the field asset. So again, please just contact me after the webinar, and I can go into more detail.
Okay. Can't keys, et cetera, be stolen through system penetration by hackers?
Can you repeat that, please?
Can't keys, et cetera, be stolen through system penetration by hackers?
Keys.
Keys.
Again, one problem with secret key cryptography is if both parties have the key, it has to be stored somewhere, if I understand your question. So not only is there a chance of compromise when the key is being sent from one person to another, but it's in storage. So a hacker can get into your system, into memory, and obtain secret keys that way. And that's a very common way of breaking into a cryptography system. So storage, again, that's a very good point that was brought up. you have to worry about protecting your keys not only being transmitted but stored in your system, which could be vulnerable to penetration.
And there are some technologies, oh, sorry, go ahead.
I was going to move to the next question, but you can go ahead and answer.
Oh, okay. There are some technologies, and if Dr. Krutz would like to expand on them after I mention them, please feel free to do so, sir. And that is, if a key gets stolen, you can have something called a public key infrastructure, which essentially allows you to add certificates onto a revocation list. So if you have someone who has access to your network initially, and they no longer work for you, or they've been terminated, what have you, you can then add their particular certificate to this list and update all of the servers and devices that need to know it, so that way no one with that particular certificate can access the network anymore. Keys can also be replaced, and I believe that there are some types of cryptography where every time a session is initiated, they use a different secret key. Or there's also ways to install brand new keys and brand new certificates very quickly in case there is a breach. Dr. Krutz, would you like to expand on that, or?
I don't have too much to add. That's a very good point. Yeah, there are certificate authorities, and they maintain certificate revocation lists, CRLs, which you can access to see if a certificate is expired. And again, certificate authorities can generate multiple certificates for you with different keys that you could use if certain ones are compromised.
Okay, next question. Is digital signature the utmost security?
I don't think there's any utmost security. Digital signatures are very widely used, but that's not to say they can't be compromised. Again, they're widely used when organizations are, say you send software from a manufacturer to an organization. It's usually digitally signed, so you will not accept it and install it into your system unless the software is digitally signed. Again, since the digital signature and the hash function are a function of the message of the total software that was sent, all the bits in it, that certifies that it wasn't changed before you install it in your system. But there are means that nothing is 100% secure. And you may have, say for example, that's why certificate authorities are in there. Say I put a public key out that's easily accessible, and I say it's David's public key, but it's really mine. So if anybody wants to send a message to David, they use his public key, but it's really my public key, so I'm getting all of David's messages. So that's why certificate authorities are put in place. Certificate authorities are like a notary, where they will verify, say a website wants to have digital certificates, the website would apply to a certificate authority. Some of the popular ones are Symantec, GoDaddy, Komodo, and they will essentially say they interview you, they make sure you're valid, and then they'll give you a certificate that contains the subject's name, the subject's public key, the name of the certificate authority, and the period for which certificate is valid. So, and that is sent by, it's encrypted with the private key of the authority. So you know that the private key of the authority, if you open it with their public key, that's a valid certificate. But then you can keep going around in a loop. You can say, well, how do I know that was really the authority. So it's a circular system. Authorities have cross-certification with other authorities to guarantee who they are. So there's not to say that somewhere in the middle of this whole operation some things cannot be compromised, but I guess the bottom line is it's very, very minimal.
Okay. Does the overhead caused by adding the encryption-decryption cause process control issues because of the delays?
Now, asymmetric encryption requires a lot more processing. So a lot of the encryption that is done over like field networks is usually some form of symmetric encryption. And from what I've seen from the lab, the lag that would be applied to a communication using asymmetric encryption, something like AES 128, would be about 150 milliseconds or less.
And I think that's very good, Dave. It answers the question, but I think it also depends on where the signal is going and where it came from. You know, in some cases, if it's a lot of data, and if we're using public key encryption, the delay could be significant. So it depends on, do you need a response time of milliseconds or seconds or minutes? The application is a determining factor. How deterministic is the system you're working with, and can you count on those time requirements?
Okay. Let's see. When we talk about involvement of IT staff and SCADA network, how much is it feasible or practical due to their limited knowledge of the SCADA system?
That, of course, depends on the company and the individual. And it might not really be an issue of training an IT guy in SCADA, but rather having a dedicated part of the SCADA department act as a security agent, a security officer. At least the SCADA I have dealt with is extremely granular. There's hundreds of details that have to be paid attention to on site. And when you're trying to bring in data, you have to have hundreds or thousands of registers from one site with the right IP address, the right port, the right HMI, everything working smoothly. And applying security to a system that is that granular, that detailed, and that essentially difficult to maintain correctly is going to be hard. There's not going to be a easy one kind of, okay, well, I just click this one setting on my computer and now they're all going to work. So I actually forgot what the question was. Michaela, which question was it again? I got lost in my own answer.
This was when we talk about involvement to our IT staff and SCADA network.
Okay.
How much is it feasible?
Yeah. So yes, the short answer then is what I would hope to see, at least in SCADA departments, is not so much someone in IT looking over everyone in SCADA's shoulder, but a dedicated part of SCADA that now operates not only with the goal of getting the information to talk, but with the goal of getting it to talk securely. So it just has to be integrated into the normal protocol. When a technician goes to a site, he checks the radio, he checks the registers, they do a point-to-point test to make sure everything that they see on their controller screen is what they said it is on the field, and they also do some sort of communication security check when they're out there as well.
Okay. Well, we have reached the end of this webinar. We have received so many questions, and I know a lot of you really want them answered. So I'll be sure to take down your question, and we'll have the presenters reach out to you directly to help you get those questions answered. And if you missed any portion of this webinar, it was recorded, and I'll be sure to get a link out to you maybe sometime this afternoon or tomorrow, so that way you can rewatch it or share it with your colleagues if you missed any portion. And as a reminder, please look at the ICS Process Control and Safety Symposium website, register, come visit all of us. It'll be a great event. And this concludes our webinar. We hope you enjoyed it. Please be sure to take the survey at the end of this webinar so we can know how your experience was today. Thank you so much.